Hi everyone, this is Ansys Lanto, and today I will talk about section 3.4, which is polynomial and rational inequalities. Okay, so let's start. Let me share my desktop as usual. All right, so open Windows Journal. So we're doing 3.4, polynomial and rational inequality. So as usual, I would suggest that you come along and take notes together with me. Yeah. I think it will help because my lectures are designed so that you can follow me when taking notes. So first of all, we're going to talk about polynomial inequality. Okay. So an example of polynomial inequality is x plus 3 times x minus 2 squared is greater than 0. All right. Now, there are two ways to solve polynomial inequalities. The first one is by graphing. The second one is we could solve it algebraically, so graphically and algebraically. Okay. Now, the most important for polynomial inequality is that we have one of the sides equal to 0. So one of the sides contains 0. Then we could determine which area do we want. So in this case, we want positive because we want something that is greater than 0. Okay. So later on, after we finish the problem, we're going to write down the summary. All right. Now, let's see. So after that, we will find the zeros by setting this polynomial equal to 0. So x plus 3 times x minus 2 is equal to 0. Now we have x is 2 squared, sorry, x is equal to -3 or x is equal to 2. So -3 and 2 are the zeros. So as we know, zeros translate to x-intercepts. So if I'm solving graphically, so here, what I'm doing is graphically, solve by graphing. Okay. I have two zeros. The first one is -3 and it's open because this is just greater than 0. So -3 is right here and 2 is right here. So if I have my coordinate system x and y, so 1, 2, 3, 1, 2, 3, 4. So 2 is right here, and it's open also because this is just greater than, not greater than or equal to. Now, if I'm graphing, the related function is f of x is equal to x plus 3 and x minus 2 squared. And I know that the degree is 3, so x times x squared. The degree is 3. And leading coefficient is positive, so 1x times 1x squared, meaning x cubed. Leading coefficient is positive, so I know that the end behavior looks like this. So it starts low and end high. Now, looking back at the zeros, we know that x equals to -3 has a multiplicity of 1. X is equal to 2 has a multiplicity of 2, so it's an even multiplicity. It will touch here at 2. So if I'm graphing this, well, my graph doesn't have to be perfect, but it will look like this. Yeah. And it crosses at -3 because the multiplicity is odd at -3, and it touches at 2 because the multiplicity is 2, which is even. Okay. Now, let's look at the plus and minuses, the sign. So, for x smaller than -3, this is below the x-axis, so this is negative. And this is positive because this value, the function value, is above the x-axis, and this is also positive. Now, since I want positive values, so let's go back to our first line here. We want positive values, then it means we want these two areas from -3 to 2, followed by 2 to infinity. So my solution here, based on my graph, is -3, 2, and then parentheses, because 2 is not included, -3 is not included, they're open circle, union 2, infinity. Okay? Alright. So that's graphically. So you could also choose to solve the inequality algebraically. So let's see how it works. So this is algebraically. So it's almost the same thing. So again, we have x plus 3 times x minus 2 squared is greater than 0. And since we want values that are greater than 0, then we know, oh, we want positive values. Okay. Now we have to find the zeros and plot them on the number line. So almost the same thing. X plus 3 times x minus 2 squared is equal to 0. So x is -3, or x is equal to 2. Right? So the same thing. If the multiplicity is odd here and the multiplicity is even for 2. Now we will graph these two zeros. So these are the zeros. So we will graph the zeros on the number line. So same thing as before, it's just that we're not graphing. So -3 and +2. And both are open just because my inequality doesn't contain equal sign. This is just strictly greater than. Okay, so now instead of graphing, we are going to do a table. So we will write down intervals. So this consists of 3 intervals, 1, 2, and 3. All right. So, and then we will take test point on each interval. And we want to know the sign. So we just want to know the sign of x plus 3 times x minus 2 squared, right? Now, we're only concerned about the sign because we want to know if the sign on such some interval is positive or negative. So let's choose a test point on interval 1. So let's just say -100. So I'm going to choose small values or very big values because I only care about the signs. Now I'm going to substitute -100 to this expression right here, x plus 3 times x minus 2 squared. So when I substitute -100 plus 3, that is minus. And then whatever number I have, when I square, it will be positive. So a negative multiplied by positive is negative, right? So the sign on the first interval is negative. Now, if I choose a number between -3 and 2, so I'm going to choose 0. And when I substitute 0 on these expressions, so I have 0 plus 3, that is positive, times positive. 0 minus 2 squared is positive also. This is positive. Now we're done with interval 2. Now the next one, maybe choose 100, like another big values. So when I substitute, I will have 100 plus 3, that is definitely positive. multiplied by 100. A number square is always positive, so positive times positive is positive. So I have all the signs for this interval. So actually on the first interval is negative, this is positive, and the last interval is also positive. So now I want positive values. So this is the interval that I choose. Now, however, at 2 here, it's undefined, so we have to really break down interval 2 and 3. So in this case, my solution will be -3, 2, union 2, infinity. Why? Because I have to break down interval 2 and 3. There is a hole here at x equal to 2. Yeah, so that's why I have to break them down. Okay? All right, so now let's take a look at a different problem. So I am going to open the next page. So number 2. Before we do that, let's just do a summary of what we do to solve a polynomial inequality and rational inequality. So summary first. To solve a polynomial inequality and rational inequality, okay, so number 1, simplify so that one side contains only 0. Okay, so we will do algebraic manipulation so that one side contains only 0. Yeah. Why is it important? Because if we have f of x greater than 0 or f of x greater than or equal to 0, then we know we want positive value, or sometimes it includes 0 in the bottom one, where in the bottom one, positive values. And if f of x is less than 0, f of x is less than or equal to 0, then we know we want negative values, or zeros, including 0, or the bottom one. All right, so that's very important. 2, find zeros. If we have a rational inequality, for a rational inequality, simplify so that the non-zero side contains one rational expression. Okay, so meaning we have only one numerator, contains only, okay, one numerator and one denominator. Okay. Now, on the third one, find the zeros of f of x. For rational inequality, we find the zeros of the denominator also. Find the zeros of the denominator. And then we have to exclude this value. So exclude the value by graphing an open circle. Yes. by using an open circle. Okay. So this is the one for rational inequality. Okay. Now, number 4, use the number in step 3 to separate the number line into some intervals, into a few intervals. Okay, so once we find the zeros for the numerator and the zeros for the denominator, we use those numbers to separate the number line into intervals. So 5. So choose a test point for each interval. And substitute the value to f of x to find out the sign. So we only care about the sign, which is positive or negative. Okay. Now, see step 1. Whether the positive or negative is needed. Then write the solutions. Okay. So we have done these steps before for the first problem when we solved polynomial inequality algebraically. So now we will do one more example. All right. Okay, so number 2, solve x cubed is less than or equal to 4x squared. So this is a polynomial inequality, and the first step is to have one side equal to 0. So x cubed minus 4x squared is less than or equal to 0. So then, on step 1, we know we want negative values. Why? Because we want something that is less than or equal to 0. Okay. Now, let's find the zeros. So to find the zeros, we just set this function on the left to equal to 0. So then we factor it out. So factor out x squared times x minus 4 is equal to 0. So 0. Okay. So x is equal to 0. Multiplicity is 2, or x is equal to 4. Okay. Now, we are going to graph these on the number line, and zeros is in the middle, so it's going to be a closed circle because this is less than or equal to, and 4 is also going to be closed. And we know that we have 3 different intervals. Now, we could choose the test point on each interval. So again, we will have a table. So interval test point, and later on we care about the sign of the expression. So sign of x squared times x minus 4. So if I have x squared here, any number squared will be positive. So the sign of x squared, whatever number we substitute in, will be positive. So let's find some values in interval 1. So interval 1 test point maybe negative 100. Yeah. Now, when I substitute it to x squared, it will always be positive, and then 100 minus 4 is positive, so positive times positive is positive. Okay. Now, in between the second interval, 0 to 4, let's just choose 2. So 2 squared is positive, 2 minus 4 is negative, so positive times negative is negative. All right. Yeah. Oh, by the way, the first one is also negative. I made a mistake. So negative 100 minus 4, that's also negative. So for the first interval, it's negative. And for the third interval is positive multiplied by 100 minus 4 is positive. So this is positive. Yeah. Now, we're going to write down that on the first two intervals, this will be negative, and this is also negative, and the third one, this will be positive. Okay. Now, let's write down the solution based on step 1. So we want something negative, so this is all the negative solutions. Okay. And 0 is also included, so actually, this is the same interval. I could write them as one interval. So since 0 is a closed circle, so the smallest solution is negative infinity, and the largest solution is 4. So in this case, we don't have to, what is it called? We don't have to separate from negative infinity to 0 and 0 to 4. Just because this 0 is a closed circle. Yeah, so it's actually continuous interval. Different from the previous problem where we have an open circle at 2. So we have to separate them into 2 different intervals. Yeah, but this one, 0, is a closed circle. All right. So I guess we are done with polynomial inequality. I guess the solving by algebraic method is probably a bit easier, but you could try either the algebraic method or the graphing method. Okay. Now we're going to talk about rational inequality. And in the summary, we know that the way to solve a rational inequality is almost the same as the way to solve a polynomial inequality. So, for example, let's solve x plus 1 over x minus 2 is greater than 0. All right, so one side, the right-hand side, contains 0 here. So, and this is greater than 0, so we know that we want something positive, right? Because we want something that is greater than 0. And also, I noticed that the left-hand side, the non-zero side, contains only one rational expression. I have one numerator, I have one denominator. So the next step will be to talk about zeros of the numerator. So x plus 1 is equal to 0. So x is equal to negative 1. All right. Now we also have zeros of the denominator. We have x minus 2 is equal to 0. So x is equal to 2. So this is the values that we exclude from the domain, meaning we have to always use open circle, regardless whether I have greater than or equal to. Yeah, so we have to exclude this value. So the values that make denominator equal to 0 always uses open circle. Now, we're almost done. We're graphing these two values on the number line. So -1, it is open because the original inequality doesn't contain equal sign. Okay, and 2 makes the denominator equal to 0, so it has to be open. Yeah. Now we have 3 different intervals based on these two values, and as usual, we will have our table. So the interval, the test point, and sign of. So we want to know the sign of, so positive or negative of x plus 1 over x minus 2. All right. Okay, so for interval 1, the test point is -100. And when I substitute to the numerator, it will be negative. And -100 minus 2, that is negative also. So negative divided by negative is positive. Yeah. And let's choose a number in between -1 and 2. And 0 is easy. So when I substitute 0 to 0 plus 1, that is positive. 0 minus 2, that's negative. So a positive number divided by a negative number is negative. And the next one is choose 100. So on top, it will be positive. The bottom, it will be positive. So positive. So I could write my signs here now. This is positive. This is negative. So I could put the negative here on top also. It doesn't matter where I put the negative, yeah, or the positive. Now we want positive values. So I have 2 intervals that consist of positive values. So that interval would be, let's write it as our solution. So the first interval will be -infinity to -1. And I'm using parentheses because -1 is not included. Union, so that's the next interval, 2, comma, infinity. So 2 to all the way to infinity. Yeah. So to solve rational inequality is not too different from solving a polynomial inequality. We follow almost the same steps. It's just that for rational inequality, you have to simplify the left and the non-zero side so that it consists only of one fraction or one rational expression. With one numerator, one denominator, then we're good to go. Okay? Okay. I guess we will do one more of rational inequality. So let's start. Number 2. All right. So 5 over x minus 3 is greater than or equal to 3 over x plus 1. Okay, so this will be a little bit longer than the previous problem because we need to simplify. One side needs to contain only 0. So I'm going to bring 3 over x plus 1 to the other side, to the left side. So 5 over x minus 3 minus 3 over x plus 1 is greater than or equal to 0. So at this point, I know that what we want is positive value. Why? Because we want something that is greater than or equal to 0. So 0 is also included, 0 and positive, basically. Yeah. Now, what we want to do next is make sure that the non-zero side contain only, hold on, let me see. Is it recording? Yes, it is. So contain only positive values, or one numerator and one denominator. So we have to find common denominator in this case, and that would be x minus 3 times x plus 1. So I have to multiply these by x plus 1 and x plus 1 here. Okay. And for the other one, I have to multiply by x minus 3 because my common denominator would be, let's see, x minus 3 times x plus 1. And we could leave it in the factored form so it's easier for us. Okay, so now let's just write. The first one is 5 times x plus 1 minus 3 times x minus 3. Alright, so now let's simplify. So this is x minus 3 times x plus 1. So 5x plus 5 minus 3x plus 9 is greater than or equal to 0. So 2x plus 14 divided by x minus 3 times x plus 1 is greater than or equal to 0. So this is the most simplified form of our inequality. So we will box this. So we could start with this one. So now let's talk about the zeros of the numerator. So 2x plus 14 is equal to 0. 2x is equal to negative 14. So x is negative 7. Okay? Now we also want the zeros of the denominator. So x minus 3 times x plus 1 is equal to 0. So x is equal to 3 or x is equal to negative 1. And these two values must be excluded. How do we exclude them? Using open circle. Okay, so I have to exclude those two values. Now, I have actually 3 values, so I will have 4 different intervals. So 0 is in the middle. Negative 7, let's see, negative 7 is close because the original inequality has equal sign in it, greater than or equal to. And negative 1 is open. Why? Because we always use open circle. We have to exclude it. And then 3 is also open circle. So I practically have 4 different intervals. Okay. Now I will have my tables again. So interval, S-point, and the next one is, okay, this one should be a little, the sign of 2x plus 14 over x minus 3 times x plus 1. So this is the most simplified form, right? So on the interval now, let me make sure it looks better. Okay, looks a little better. So we have 4 intervals. 1, 2, 3, 4. Test point on the first interval is anything less than negative 7. Okay, I'll just put negative 100. So on top, numerator, when I substitute, it will be negative divided by negative times negative. So this is negative on top divided by positive, so this is negative. Yeah. The second one, let's see, between negative 7 and negative 1, so maybe negative 5 or negative 4. Okay. So when I substitute 2 times negative 4, that's negative 8 plus 14, that is positive. divided by negative 4 minus 3 is negative, negative 4 plus 1 is negative. So positive divided by positive, this is positive. And between negative 1 and 3, 0 is in between, so maybe use 0. Oh, sorry. So we use 0. So the top one is 14, so positive divided by negative plus multiplied by positive. So positive divided by negative, that is negative. And the last one is 100. So we have the top is positive, and then 100 minus 3 is positive, 100 plus 1 is positive. So this is positive. So a positive divided by positive on the bottom is positive. So let's write down the sign on our number line. So this is plus. Oh, I'm sorry. The first one is negative. On interval 1 is negative. I could put it down or top. I could just put negative here. It doesn't matter. The second one is positive. The third one is negative. The fourth one is positive. So let's see which one. Do we want positive value? Yeah, we want positive value. So we choose this one, and we also choose this one. There are two intervals containing positive values of function. So let's write down the solution. So I'm going to write it here. So solution for positive values is negative 7 to 1 union 3 to infinity. So these two intervals. Okay? Yes, this problem is a little longer than the first one, but the principle or the way to solve a rational inequality is always the same. So first of all, we want one side to contain only 0. Then we simplify the other side so that it contains only rational expression, one numerator, one denominator. And we find the zeros, and we have the table. And then after we know the signs, we look at step 1 back, whether we want positive or we want negative. And we write down the solution based on step 1, where we know if we want positive or negative. Okay, I guess that concludes the discussion of polynomial and rational inequality. Please try again and feel free to pose questions on discussion board topic questions and answers. Okay? All right, I guess I will see you next time. All right. So that's it. This is polynomial and rational inequalities. See you next time.